Hello everyone, welcome to series of video on expectation maximization algorithm, a coin flip model. In the last video, uh, we calculated the marginal probability of observing this experiment 1 given the value of theta A, theta B and the mixing proportion. So this is where we have stopped in the last video. Now let us generalize this formula. So similarly, for the experiment 2, the only thing which will change is the number of heads and number of tails. So the probability of observing experiment 2 given the parameters is something like this. The only difference from here to here is the number of heads and number of tails. In the first equation, the number of heads is h1 and that for tail is t1. In the second equation, number of heads is h2 and that of tails is t2. Now similarly, we repeat this experiment for m times. And then we say, okay, we have done the m times of experiment, m number of experiments. This is the observation. Now all the experiments like experiment 1, experiment 2, experiment 3 and so on, all these are independent to each other. Like observation of experiment 1 does not influence the observation of experiment 2. So the likelihood of the complete set of experiment observation will be multiplication of all these values for m experiment. And so we can write that as L for likelihood is probability of observing the experiments given the parameters is multiplication. It is indexed by J, which varies from 1 to m of the observation for each experiment. Multiplication of the probability of observing a particular experiment up to m. So this is what is the likelihood for the complete experiment. When we say complete experiment, it means E1, E2, E3 till EM. Now for simplification of calculation, let us substitute this as Kj. So this equation can be written as something like this, where Kj is this one. Now to find the value of the theta and alpha, mostly we are interested to find the value of the probability theta. We need to maximize this likelihood. Means which value of parameter will maximize the observation of the experiment. So as little bit of calculus here to maximize the value of any function, we have to do the differentiation and equate it to 0. But there is a challenge that because we have here a multiplication, so generally differentiation of multiplication follows a chain rule. To avoid that complication, what we do that we take the log likelihood. Log likelihood is logarithm of this one, and we maximize that. So the parameter which will maximize the log likelihood will be the parameter which will maximize the likelihood as well, because like log likelihood is nothing else but simply a mathematical conversion what we are doing. So to maximize, in the maximization step, what we do that we take the log likelihood. So when we take the log likelihood, this multiplication term gets converted to summation. That's the basic of logarithm function. So small l is the log likelihood equals to logarithm of the likelihood, that is summation of log kj from j is equal to 1 to m. And then as we have to establish the value of theta a, theta b, alpha and alpha b, so now we have to differentiate this in respect to each of the parameter one by one. To get the maximization value for theta a, we need to differentiate this function in respect this derivation in respect to theta a. So and then equate it to 0. So partial derivation of the log likelihood in respect to theta a equated to 0, and we have to get the value of theta a from here. So let's evaluate this one. Now for ease of calculation, let us derive first derivation of log k1, and then we can generalize that for log k2, k3, k4 and kj. We can generalize that once we get the value for the partial derivation of the log k1. So the task here is, let us find the partial derivation of logarithm of this function. Now this can be expanded as, we are expanding this value, the summation function. So logarithm of alpha a, logarithm of this function. This is nothing else but k1. If we recall, this is k. Now, after this, to get the differentiation of this equation, we'll have to refer a bit of basics of calculus. And one of the differentiation formula what we find in calculus is something like this. Differentiation of log of function of x in respect to x is equal to 1 divided by function of x multiplied by differentiation of function of x. Now function of x, let us make a similarity from this established formula from calculus with what we have to do here. When we make the similarity, the function of x can be mapped to k1, right? So function of x is this one. So when we differentiate this, the result will be 1 by k1, then partial differentiation of k1, this part, sorry, this one is 1 by k1 and this one is differentiation of k1 in respect to theta a. So once we expand it, we will get 1 by k1, then differentiation of k1. Now to proceed further, we have to refer another basic formula from calculus, and the formula is differentiation of a constant multiplied with function of x is equal to the constants comes out and then differentiation of function of x. So now if we see here, now this term does not depend on theta a. Theta a is not a variable in this particular formula, the formula what I've highlighted here. So differentiation of this function, this derivation in respect to theta a would be 0. That's what I have written here. Now let us work out to the next rest of the term. So 1 by k1 comes as it is. Then alpha a is a constant. Alpha a does not depend on theta a. It's a constant in respect to theta a. So alpha a comes out. Alpha a is mapped to m here. Then we have to differentiate this function. After this, to proceed further, we have to refer another basic formula from calculus, and this is something like this. Differentiation of function of x into f of x into g of x. There are two different functions of x and both are in product here. So to differentiate this, the formula is function of x into differentiation of g of x plus g of x into differentiation of function of x. Now let us map this formula to this place. Function of x can be mapped to this term because this is one function depending on theta a, and g of x can be mapped to this term because this is another function of theta a. Now following the formula. So 1 by k1 comes as it is, alpha a comes as it is. Now we have to differentiate this formula. So first function comes as it is, then partial differentiation of the second function plus second function comes as it is, then partial differentiation of the first function. After this, to proceed further, we have to follow another formula from calculus, and this is something like this. Differentiation of function of x to the power m. Sorry, there is a mistake here. Let me put it properly. So this one is equal to, this m comes here, m multiplied by function of x to the power m minus 1 multiplied by differentiation of function of x. Now let us map this to this one. So this is the function of x, assume this 1 minus theta a is function of x to the power m, and in this place the function of x is theta a and to the power h1, that is mapped to m here. So let us work out this one. 1 by k1 comes as it is, alpha a comes as it is. Now let us differentiate this one. So theta a h1 comes as it is. Then when we differentiate this function, t1 into 1 minus theta a to the power t1 minus 1, and then this is same as this one, and then we have to differentiate the function of x. Then we have to differentiate 1 minus theta a. So when we differentiate 1 minus theta a, the negative terms comes here. That's why we have this complete function, this complete derivation. Plus, now let us work out for this one. 1 minus theta a to the power t1, then h1 is mapped to m, and theta a to the power h1 minus 1. So this completes the differentiation of log k1. Due to time consideration, I have to stop my video here. We will catch up from this place in next video. Thanks for watching. Please follow the next video.